We have that. So that's by welcoming everyone at 6 o'clock. Welcome to our second online Café Scientifique. For those of you who are new to Café Scientifique and especially new to the platform, welcome. So this is a continuation of Café Scientifique in person, which is where we meet twice a month at Herman's Jazz Bar, and UVic researchers tell us about the science they're doing in plain language without overhead slides. Now, obviously, we've all had to adapt recently, and so we're not in a jazz bar anymore, and we've allowed our presenters the luxury of PowerPoint. So if let me give just a quick tour for those of you who are maybe unfamiliar with Blackboard. At the bottom of the main panel, you have your controls. You can see your microphone, your video, and your ability to raise a hand. Don't worry about your microphone. I've actually taken the privilege of using audio away from all of you, so you don't have to worry about juggling your audio, which buttons to press, so you can just enjoy the talk. If you would like to ask a question during the talk, please feel free to use the chat window, and you can access that by pressing on the purple tab in the bottom right of your browser, and that will open a window, and there's a speech bubble there. Click on there and you'll see the chat session if you want to. So one of the great things about Café Scientifique is how interactive it is. So if you want to try and ask something during the talk, please feel free. And if it's appropriate and Olav feels able to, he'll see if he can address that. What we will also do is we will probably, the talk's going to go for about 40, 45 minutes. And so around about 6:50, Olav is going to wrap up and we'll have about 10 minutes of moderated questions at the end. And the way people seem to feel most comfortable about asking questions is through the chat window. So that's my recommendation to you to ask questions at the end. So with the introduction and the logistics out of the way, let me introduce you to tonight's speaker, Olav Krigolson. Olav is a professor of neuroscience in UVic's School of Education and Exercise Science and Physical. Sorry, why don't you tell them where you're from? I made sure I practiced it, Olav, but I've forgotten now.
I've got it's fair. I've got a weird position at UVic because I'm split between 3 departments. So I'm actually recently promoted to professor in neuroscience, medical psychology, and exercise science and physical and health education.
That was what I was after. Congratulations on that.
Yeah, thank you. It's I should have changed it for this talk because it would have been my first chance to use it.
So that's your introduction to. One thing I have to say to the audience as well before we start is Olav. Many of you know Olav as the co-host of Café Scientifique. He often deals with those that are organized by the Center for Biomedical Research. And despite the twin roles we have never met before. So this is actually our first opportunity to do a presentation together. So I'm very glad to finally make that, Olav.
I am too, John. Thanks for that.
Yeah.
That would be nice to meet you too.
With no further ado, let's let Olav tell us about Destination Mars, using neuroscience to improve astronaut success in outer space. All yours, Olav.
Okay, well, good evening, everyone, and thanks for tuning in. This is a version of a talk that I gave live a while back about some research that my lab and colleagues of mine did in the Mars habitat in Hawaii. And this talk's really also going to be sort of the backstory behind it and where we're at today. So I'll begin. And I'll start by asking a question that I think about a lot, which is, what could we do if we could peer inside the mind? And what I mean by that is actually measure the brain in real time and see what people are thinking and doing and use that information. And that's really the problem that I've been trying to solve is how can we measure brain activity and use that activity to do any number of things. In this case, it's work that we did to help NASA in preparation for the Mars mission, or to be fair, any other long-duration space exploration missions. So how do you do that? How do you peer inside the mind? There's a couple different ways to do that. And really what you want to get at when you do that is this. You want to get at neurons in the brain, because your brain is made up of neurons. There's other tissue in there, but all of the bits that have to do with thinking and are the product of neurons firing in your brain. So as you think and you decide to do something like have something for dinner, that decision is a product of neurons in your brain firing. And as things happen to you, for instance, if you get mentally fatigued or you get stressed or you get depressed, that is represented by patterns of neural activity from all of these neurons in your brain firing. And really what we want to do is if you can measure that, you might gain insight into these states and be able to detect them and possibly even monitor ways to change them. So how do you do that? Like I said, how do you measure these neurons and how do you peer inside the brain? Well, one way you can do that is EEG, or electroencephalography, or what a lot of people just simply call brainwaves. So EEG is a relatively old technology. It was first developed in the 20s. Hans Berger gets the credit for the first human EEG recordings. And essentially, it's pretty straightforward. A lot of people are familiar with hospital shows where you put electrodes over top of the heart muscle, for instance, and you detect the beat of the heart. And really what you're picking up is the electrical activity of the muscle contracting. EEG is similar to that in the sense that you put electrodes on the head, and if you use very fancy electrodes that have a really good amplifier, you are not picking up muscles contracting, although you see that as well, but you're actually picking up the summed electrical activity of all those neurons in the brain firing. And EEG used to be done kind of like this. Rick is wearing what I would call a traditional EEG cap, somewhat similar to what you might see in a hospital or a research lab like mine. These EEG caps and the systems with them aren't cheap. They cost in order of $75,000 to $150,000. And the problem with them is obviously getting that on is a bit of work. So it makes peering inside someone's brains a bit tricky. And that'll be one of the themes throughout this, is how we've sort of taken this kind of technology and made it mobile in a sense. Now, if you do this, the question is, what do you see? And you see this. So what you're looking at is the human electroencephalogram. The big bumps that you see aren't anything too exciting. That's actually someone blinking. And it's the little tiny bumps that you can barely see here. And I'm not sure if I can get away with a finger. I don't know if you see it, but if you do see it, these little tiny ridges in here are the neural activity that sort of reveal thought processes, and these big massive changes that you see are muscular artifacts. And if you measure this from a bunch of electrode sites, that's kind of cool because it gets you to this. So this is someone thinking. As the colors change, it's literally the electrical activity of different groups of neurons firing. And this is really what we're trying to decode, is these patterns. So these patterns reflect a whole bunch of different things. For instance, in this case, a lot of the activity had to do with someone making a decision. But while they were making that decision, there was a lot of underlying things happening. They might have been tired, as I mentioned earlier. They might have been stressed. And all of that sums up to a pattern that you have to decode. And it's funny because when I started out, I was actually a physics undergraduate, and I taught high school for a while, and I taught mostly physics and math. And then when I went back to school, I got into neuroscience. But I like to tell people that a lot of what I do now is math, because it's really thinking about ways to identify these patterns and decode them into something that's meaningful. So if you can peer inside the brain and measure these things, you can potentially do some pretty cool things. Here's an attempt of decoding the patterns, and what you see is 4 different brain states. So this is from a large array EEG system. The little black dots are the electrodes, and these all represent slightly different brain states or thought processes. And really what we're interested in doing is, if you can measure this, you can decode these patterns and potentially provide some performance feedback. So you could look at brain health and performance, which is really how this ends up tying into NASA and the Mars mission. So right now what I'm going to do is I'm going to get you to play a simple game. Some of you have seen this game before. You're going to see a bunch of circles. What I want you to do is count the green circles. You're going to see blue circles as well, but ignore those and just count the green circles that appear on the screen. So hopefully you got to 3. And the reason I got you to play that game is really simple, is that it's an easy way to evoke a specific brain pattern. So for instance, if I looked at your brain's response, well, if I happened to be measuring the EEG in your brains right now, and I looked at your brain's response to the appearance of those green circles, I'll see something, and we call that an event-related potential. Essentially, you're looking at a graph where the y-axis voltage and the bottom axis is time. You'll notice the unit is milliseconds. It's a very rapid response. And typically what you see is you see a pattern that looks something like this. Now, this is from a single electrode site, which is why it doesn't look like the fancy swirling maps you saw earlier. But this is a really well-studied neural response. And it's kind of cool because this response is sensitive to a bunch of different things. As you'll see as we go through this, this is one of our primary tools for measuring cognitive fatigue, and I'll talk a bit about that in a second. So you're going to measure EEG, and you're going to get these responses. As you saw earlier, we've been lucky in my lab. We've had Rick by. This is Bob coming in to learn a bit about mindfulness. But this is how we used to do this. What if you could do it with this? So this is a Muse EEG headband. You can buy them online from Amazon, preferred shopping method, or if you went down to Best Buy and were able to go in and order, they're on the shelf in Best Buy. And the Muse is an EEG system. As you can tell, it's pretty simple to put on. I mentioned earlier that with the large array system, the setup time is in the order of 45 minutes to an hour. With this, the setup time is about 25 to 30 seconds. It just slides onto your forehead, and the pieces on the right-hand side of the screen tuck in behind your ears. And it's cheap. This costs about $249 last time I checked. So does it measure EEG? Is this a viable solution for the big array system? And the question is, it does. Some of our first work with this kind of technology, which we now call mobile EEG or MEEG, we published this in 2017. It's work we did here at the University of Victoria. And we basically put the Muse headband head-to-head with our $100,000 system. And I've always liked the results of this paper because a lot of you realize that when we do research, we use a lot of statistics to analyze our data. But in this case, we didn't need to do a lot of statistics. If you look on the left-hand side, that is the EEG response from our standard $100,000 system. And if you look on the right, that is our EEG response from our $249 system. And they're a little bit different. They're not identical, but the general pattern is the same, and it's good enough for us to peer inside the brain and sort of do the sort of detection that we want to do to measure various aspects of brain health and performance. So how does this all relate to Mars? I dropped Mars at the talk, and for the past 10 minutes or so, I've been talking to you about mobile EEG and brain waves and things. Well, NASA is working under the premise that they're going to be making a mission to Mars. They've been told that by 2 successive governments, and it's going to be a challenging mission. So why is that? There's some very obvious reasons, obviously. For instance, getting there is an issue. Mars is quite a distance away. We've sent probes there, but to get a human crew there and spaceship is going to be challenging. There's the idea of radiation. We all know that too much radiation is bad for us, but in terms of a Mars mission, people are going to be exposed to radiation for a couple of years. A projected Mars mission has a duration of about 3 years. A year to get there, a year on the surface, and a year to get home. There's the issue of a low gravity environment that astronauts spend, and especially when they're in outer space, spend a lot of time exercising because they're trying to offset the effects of low gravity environments. There's an issue of resources, for instance. If you go to Mars, everything that you need, you have to bring with you, at least currently. Obviously, they're working on solutions to potentially mine some stuff to help support an extended mission. There's the distance from Earth issue. Communication time to Mars takes about 20 minutes on average. So if you send an email or a radio message to Mars, it takes about 20 minutes to get there. Then the astronauts have to read it, and then they have to reply and send it back. So you can imagine that this conversation lag creates a lot of problems. For instance, you might miss your family or friends just getting instructions in case of an emergency. And there's another big issue, and this is really where we come in, because as much as I'd like to think I could help solve the first 5 problems, I'm not an engineer. My job is as a neuroscientist, as you know, and the human factors are quite simple. The long mission duration has a lot of negative impact on brain health and performance. The work that's been done on Earth already, and this is where I'll get to, where they do analog missions. So they take astronaut-like crew and they put them away and lock them away for an extended period of time. That creates a lot of brain health problems, something that we're kind of going through now with COVID to some extent. And that pairs directly into this, the issue of isolation and being away from others. And I think we can all appreciate that one. The time delay, as I mentioned, creates a communications problem. And really all of this adds up to things that have a negative aspect on brain health. So why does that matter? Well, simply put, this is a picture from the high seas habitat in Hawaii, but imagine this is an astronaut on Mars, and imagine that they're cognitively fatigued. Their brain is tired and they're making some bad decisions. Well, if you slip and fall here on Mars, you're dead. You could get a tear in your suit and you'd die instantaneously. And this is a real problem that NASA faces, is that they're going to put astronauts in extremely stressing environments for long periods of time, and they're bound to get cognitively fatigued. And when they get cognitively fatigued, they're going to make these mistakes. And if they make those mistakes, crew members will die. So cognitive fatigue is a massive problem. This is why NASA cares, is essentially this slide here. This isn't work from my lab. This is work from a different lab. But on the right, you're looking at basically the relationship between human performance and blood alcohol concentration. And as we all know, performance drops the higher the blood alcohol concentration. And that's why we have rules against drinking and driving. What's interesting is hours of wakefulness, fatigue, in other words, result in the same drop in performance. And this is what we're talking about, is if you put people in states that create this sleep deprived or mentally fatigued state, then you're going to get drops in performance comparable to if someone is impaired with alcohol. And that, of course, is a problem. So basically, the mission that my lab and our collaborators are undertaking is, can you develop a mobile assessment of brain health to support astronaut success on the Mars mission? So if you dug around on the NASA website, and you could try this yourself, you would find information on what they call their HERO program. And it's just a grants program where they're looking to solve these issues. And specifically, if you look at topic C in the HERO program, you would see that this is one of the things that NASA has outlined as critical for any long duration space mission, whether it's to Mars or somewhere else. So really what we've taken on is, can we develop this capability to do a mobile assessment of brain health to support astronaut success during space exploration? And I think you've already seen the pieces. I've basically told you about the fact that EEG is a cool way to peer inside the brain. I've shown you some evidence that you can do this with mobile EEG. So as opposed to bringing along a $100,000 EEG system and a big computer and having a testing time that might be an hour and a half or 2 hours, you can use mobile EEG, where you can do these assessments off of an iPhone or an iPad with a very cheap headband in literally a couple of minutes. So what I'm going to do for the next bit is tell you a bit more about this, and then we'll get to our Mars mission. So where we're going to end up is here. This is the high seas habitat in Hawaii. Basically, it's where one of the sites that NASA uses to study these kind of problems, so humans factors problems. So crews have been going into the habitat for almost a decade now. They go in for missions anywhere from 1 week, which was our mission, to months, to in one case a year. And really the whole environment is designed to study what happens to humans when you isolate them this way. And when you're in high seas, if you go outside, you have to wear a spacesuit. You can't just walk outside for a breath of fresh air. And the solar array is life, in the sense that on Mars, if you lost power, you would die. In high seas, I can tell you from personal experience, you just get really cold at night if you run out of power, but it's still not pleasant. So the question we developed is using an environment like high seas, can we demonstrate and can we use mobile technology and neuroscience to develop this incredibly accurate assessment of brain health? And that's really where we're going. So what I want to do is give you a bit more background, and then I'm going to walk you some of the research we've done over the past couple of years, and then I'll tell you about what the future holds. So I showed you that brain response you can get from EEG. Remember, if you saw the circles, I showed you that you had an evoked response. In this case, the uncertain circle was the green circle. Really, it just means that it's important. But if you peer around on the screen, you'll see that this isn't new science. We didn't discover the brain response to those circles. This was discovered by Sam Sutton in 1965. So the actual neural responses we're looking at have been known about for quite a long time. More recently, we've become to understand them even more. I'm not going to take you through all of this, but if you trust me on this one, basically the cortex, and if you look on the top right, it says P3. That is the neural response that we observe is called a P300, which is P3. But people have mapped out the underlying neural system that contributes to that neural response. And we have a pretty good understanding of what specifically results in seeing that ERP I call it an ERP, an event-related response that you saw earlier. Now, why do I care about this specific response in this case? Well, it really boils down to this. If you think just about the cognitive fatigue problem, it's pretty well known that that brain response that we get in that little circle game is reduced when you're cognitively fatigued. And it's really that simple. The science behind this is basically you get someone to play the circle game on an iPhone or an iPad. You measure EEG through a low-cost device because it's easy and fast to do. And you track these neural responses, and you can use them then to gain insight into whether someone's fatigued or not. So really what's changed is not our knowledge of the underlying brain patterns, although we learn more about that every day. It's just the fact that this technology has gotten mobile and easy to use. So when we started this project, we really thought, let's start at the beginning. Let's make sure we can measure cognitive fatigue. If you read a bunch of scientific journals, it appears pretty clear that we should be able to, but I like to try to make sure I can do it myself and see it for myself. So these are data from the University of Victoria. On the left, you've got our control subjects. These are people that are rested. On the right, you've got people that are fatigued. And you'll notice that this is the P3 response there. You'll notice it's greatly reduced in our fatigue group relative to our control group. This is basically a replication, but it's cool because it means what people have reported in the literature, we clearly saw in our own data, which is always a good thing to see. So our first study was just testing a bunch of students at the University of Victoria and demonstrating that we could do this with a Muse. So experiment 2 in this series was we wanted to get out into the real world and see if we could do this in environments where it could be useful, because NASA isn't the only problem we're trying to solve, but also to get some validity on the testing method. So the first of these studies happened here. This is the clinical simulation room at the Royal Jubilee Hospital. These are Island medical students working on a robot patient. And they basically one of the things they do is called a night on call, a simulated night on call. So they basically have to run into this operating room and operate on these patients or make a diagnosis and do the correct thing. And they do this on and off for 12 hours at a time. And our underlying assumption is that at the end of the 12-hour shift, they're probably more fatigued than they are at the start of the 12-hour shift, one would hope. So we repeated this, and this is our early days. This is many years ago now. And you'll notice the muse on the medical student's head. It's the medical student in yellow. This is one of my former students, Harvey House. This was her master's thesis research. And back then we weren't using iPads or iPhones. We were just doing this on laptop computers. And Harvey took on this project. She wanted to see if we could measure fatigue in these medical students in a very real environment. And even though we're using the laptop, the assessment still took, at this time, it took about 8 minutes. We've cut it down over the past couple of years. And of course, we could do this. I'm just looking at the difference in the response, but the dashed line is the pre-shift, the solid line is the post-shift, and here you see that decreased neural response that indicates that the medical students were getting tired. So this was good because it meant that we replicated what we did in the lab, but we did it in the real world. So another step in the right direction. Experiment 3 was we wanted to make it mobile. So as you saw in the last picture, we were tied to a laptop computer. So we worked in conjunction with a company here in Victoria, Suva Technologies, and specifically programmer Mark Aldred. And what he did is he developed Peer. Peer was the iPad or iPhone version of the circle game. And it basically meant that we could do this literally anywhere. So in experiment 3, we had testing sites like parks, shopping malls, cafeterias, and we were literally just grabbing people off the street whenever we could. And we were testing to see how tired they were. And lo and behold, we found our reduced response on average. But what I want to show you quickly, and you have to forgive me, I've realized right now one disadvantage to an online talk is I can't see my next slide, but that's okay. But what I want to show you quickly, because for the rest of the talk, you're just going to see scores. So what we do is we take that little bumpy waveform, the brain response, and we just turn it into a number for simplicity's sake. Now, it's not quite as simple as what you see here, but you're not going to see any more brain waves, and I just want to explain that transition quickly. So here is our data from all these people. Basically, we find that people get more tired the longer they work, and this is the pattern we also see in the EEG data, that we can replicate this trend. So experiments 4 and 5, we wanted to leap back to the real world. In this case, we wanted to get extremely applied, so I'll show you 2 of these studies quickly before we move on to Mars for the last bit of the talk. We went back to the Royal Jubilee Hospital, and in this case, we weren't working in the clinical simulation room. We were actually set up in the emergency room. So this is a room at the back of the emergency room, and you're looking at one of the nurses, and she is undergoing our test on an iPad during a break in her shift. So we wanted to prove that we could do these fatigue assessments in the real world and with real people in an even more, what I would call, ecologically valid context. And I'll show you the results a bit differently this time. I'm going to talk about some people. This is what we sort of expected to see, a pre-shift and a post-shift score. Blue is good, purple is tired. And we would expect over the course of 12 hours in the ER that people get tired. Here is someone we measured 4 times, even better at the start of their shift, a couple of mid-shift scores, and by the end of their shift, they were down. Here's another person, very, very similar to the first, only small differences that you really basically need a ruler to see. But here's an interesting case. Here's someone we measured where at the start of the shift, they were rested. In the middle of the shift, the purple circle, they were tired, but at the end of the shift, red means you're exhausted. So this is a case where someone was probably doing their day job in the emergency room, but maybe they shouldn't have been doing it. So you might start to see why you might want a fatigue detection system, because in principle, you could use this technology because it only takes a couple of minutes, and this person maybe shouldn't be doing their job. Here's another example. Here's someone that was tired at the start of their shift. And you, again, you could imagine that if someone shows up for work and we know they're tired, especially in the emergency room, should they be working? So this was cool because we saw the tech working the way we hoped it would work in the real world. I'll tell you quickly about a second study. We basically replicated this in a mine in northern British Columbia. So I took my lab up there and we were testing miners. I won't show you individual results this time, I'll show you trends. But here are fatigue scores for the mine employees we tested. We tested a couple hundred mine employees, and basically, if you know a little bit about statistics, you'll know that this graph is what we'd say is skewed. There's more scores on the bottom half than there is in the top half. And ideally, you would expect most people to be average in the middle, about a 3. So what we found out was that all of the miners were exhausted. Or not all of them, but at least a large percentage, which of course is not a good thing if you're interested in mining safety. I'll show you another interesting graph, and I'll preface it this way. The miners work 7 days on and 7 days off. Think to yourself quickly, on a 7-day work schedule, what days are you most tired? So here's what we found. They were most tired on day 7, and they were tired on day 6. But interestingly, they were also tired on day 1. And the reason for this is simple. After 7 days off, they just weren't ready to go back to work. I can only speculate on the reasons why, but what's interesting about this specific data is it also parallels the accidents that you get in one of these mines. They get most of their, excuse me, most of their accidents on day 1 and day 7. So, finally to Mars. I've given you a heck of a backstory. I've told you about EEG and why you might want to measure it. I've told you about mobile EEG. I've told you a bit about our background research, and that basically led us to our project at High Seas. So, as I pointed out, NASA is extremely interested in this, and our first contact was they gave us a 1-week mission as a proof of concept. So, they wanted to see our fatigue detection technology work in the same environment that they're going to do the next Mars simulation in, and an environment that's akin to what happens in at least potentially on the surface of Mars. So in December of this year, last year, sorry, I took a research team to the High Seas habitat for a 1-week mission. The crew was myself, Dr. Gordon Binstead from the University of British Columbia, Okanagan, Dr. Kent Hecker from the University of Calgary, 2 collaborators of mine, and 2 PhD students from my lab, Chad Williams and Tom Ferguson. And really our goal was to just basically pretend to be astronauts for a week and see if our fatigue detection system worked, if it worked in this environment. This is a view of High Seas. High Seas is located on the big island of Hawaii. It's in the middle of a volcanic field, and it's very isolated. To walk from High Seas to almost anywhere would take you a long time. It's also conveniently on a military base to prevent trekkers or hikers from wandering in to see what's going on there. The habitat itself, this is a schematic of the habitat layout. I'll take you through it a bit closer, but the inside looks something like this. On the top half of High Seas, you have the bedrooms. It's designed for a crew of 6, and everyone has their own bedroom. There's also a washroom upstairs. On the lower level, you'll notice in this case, the crew had demonstrated it with a police call box. The crews tend to have a bit of fun when they're in there for long periods of time. Around the corner from the call box is the downstairs washroom and the shower. Behind that is a wet lab for scientific analysis, the kind of stuff that you think of when you think of microscopes and test tubes. And then it's a pretty open area, and the reason for the open design is simple. They want to be able to reconfigure the space as needed. So in this case, for instance, you can see the treadmill is folded up over by the window, but if you want to exercise, you could pull it out to the middle of the room and do your exercise. Tucked around, just sort of opposite the treadmill to the left of the screen that's pulled down, is a kitchen, because one of the first High Seas studies realized the importance of the kitchen. We sort of have this adage, right, that all good parties end up in a kitchen. Well, in this case, what they realized was that the NASA's approach to food prior to this was freeze-dried meals. So you'd whip out a bag that might say spaghetti and meatballs, and you'd reheat that, and away you would go. They realized very early on that it made far more sense to give the crew the ingredients to make spaghetti and meatballs, which if they did, they had those ingredients, and they had the ingredients to make steak and potatoes, and they had the ingredients to make stir fry. You can combine all those ingredients into an infinite number of combinations. And it turned out that that had a massive impact on mental health. Here's a close-up of the kitchen area. And like I said, a social hub of the high seas habitat. Also an area you got to keep an eye on. Power is everything when you do these simulations. The simulation is intended to be extremely real, as I've mentioned a few times. So in this case, you're constantly tracking power because if you use the microwave too much, for instance, or the stove too much, you run out of power, which in the simulation sense just gets you a failing grade, but in real life would be quite dangerous. Individual workstations for the crew members. Everyone's got scientific duties. A lot of people ask me, what were you supposed to do each day? Well, basically, a day in a Mars simulation is supposed to be a day on Mars. So you wake up, you get dressed, you make breakfast, and then everyone has assigned duties for the day. If you're inside the habitat, those duties include research, they include exercise, they include meal prep, and they include maintenance. So you have to be self-sufficient and keep the hab functioning. Some of you might also have been wondering that this doesn't look much like a spaceship. High Seas is designed to simulate the space requirements and constraints of a Mars habitat, but it's not the actual Mars habitat. That is yet to be built. So this has been built to a size specification that NASA has provided, and that basically said, we can get this much space to Mars. You tell us how to design the inside because we're not sure. The upstairs looks something like this. Those are the bedrooms. They're not very big. It's a pretty small space to be in, but the bedroom becomes important because it's really the only place where you can get any kind of privacy when you've got 6 crew in such a small place. And it's also the only place where you can sort of have your personal effects, if you will. View from outside High Seas. I can tell you from personal experience, although I was only in for a week, I spent a lot of time staring out that particular window. Here is our crew out and about. This is the other thing you do. So I told you a bit about what simulation is supposed to be like inside. When you're outside, you're supposed to be doing the kind of research that the astronauts would be doing on Mars, which basically means mapping expeditions and a lot of geology. So we spent our time on the outside part of our schedule mapping out the lava tubes in the area. And that's what the crews at High Seas do to simulate what they would be doing on the surface of Mars. The other thing you do when you're outside is maintenance. The systems break and you can't call the repairman. So essentially, when you're outside, you get checklists and there are things you have to run through to make sure that all of your equipment is functioning correctly, which of course is what they would also be doing on the surface of Mars. A particular import here was the batteries. This is basically our solar unit, and one of the big things we did every day, if you look closely, you'll see on the right-hand side it says absorbing, which basically meant we were getting power into the solar panel, which was a good thing. Screenshot, the whole thing is computer controlled so you can monitor all the systems. The results of one of our meals, this is my PhD student Chad Williams, who took all those ingredients that I'd mentioned earlier and made freeze-dried pizza. So every ingredient that you see there came from freeze-dried, prepackaged food. Me exercising, not the best picture, but you get the idea. Our crew heading out across a lava field on exploration mission. Us going down inside a lava tube to map it out. You'll notice the spacesuits, they're not real spacesuits. They're overalls with a backpack, but we do have these modified motorcycle helmets and we are on an air supply. So it was heavy and awkward to move in. Again, at this stage in the game, they're not testing actual spacesuits because they're extremely expensive. So all of this is simulation. Exploring deep inside a lava tube, not a great place if you're claustrophobic, I can tell you that. I'm not, but one of our crew members was. Us doing some upkeep on a NASA experiment. Playing with a rover. This was kind of fun. We got to play around with a prototype drone rover that was used outside because obviously far safer to send this thing out to explore than to go out yourself. Now, it doesn't look very sophisticated, and I'm not an engineer, but I can tell you that they were extremely curious in this case about the wheels and the way that the axles and the drivetrain worked, and that's about as far as my knowledge goes. And what we were actually there to do. So this is us monitoring our brain health and performance. So as I said, what we did is we did that little test that I showed you earlier. We did it 3 times a day, morning, noon, and night. And the idea was it would give us some insight into our cognitive fatigue changed over the course of 1 week. Now, in 1 week, we were just hoping to collect data to show it worked. But you could imagine over the course of a 1-year mission or a 3-year space mission, we could use this data to see if an astronaut was actually having a problem. So for instance, if someone's score started dropping away, we could say, well, hey, astronaut John Smith is mentally tired and needs a day off. And here are our results. Funnily enough, we actually did get fatigued. This is a bit of a busy graph, but you'll see that there's days 1 through 7, and each day our fatigue scores increased. This is the product of a 16-hour workday. So we were most rested in morning, we were a little bit more tired at midday, and by evening we were exhausted. And across the week, we were also exhausted because we had no downtime, which wasn't normal for this type of a mission. So this was really what we went there for, was to prove that we could track fatigue within this kind of an environment. This is our crew. I forgot to mention one of our crew members. Because we were only there for 1 week, we had Michaela Musilova. She's actually an astronaut trainer who works with NASA and the European Space Agency in there to keep an eye on us and tell us all how it worked. So I'll just tell you a few things as I move into wrapping up here. You might wonder how this tech is supposed to work. Well, here's how it's supposed to work. We can measure those brain scores I told you about, and you can imagine that if we measured each of you over the next week or so, there'd be a bit of variability in those scores. Some days are better than others. And we'd get a feel for what your normal brain health and performance looks like. And we'd be able to build up a confidence region indicated by the red dashed line where we say this is sort of the range of normal scores. And then you could imagine what happens if you get a score that's slow. Well, that's when we'd say, well, hey, this person's fatigued, something is wrong. So the way this would work with the astronauts would be they would be doing their assessments every day. And before they go into outer space, we'd build up this baseline and get a look at what rested looks like. And we had monitored this over time. And then if we saw a score like the one on the end, on the far right, would go, hey, astronaut John Smith or Jane Smith is having a problem. Someone needs to intervene and speak to them. Now, this is really, really important because I just ask you this. Do you think that astronauts are the kind of people that would accurately report self-fatigue, or medical doctors or pilots or any of the other environments where this tech might be used? And here's some data just with me, just so you can see sort of what it looks like. These are 2 of my tests from a couple years ago. And if you look at the blue and purple circles and bars on the right, you'll see that my scores sort of go up and down as I progress across a bunch of tests. In this case, nothing that's dropped off the bottom and being dangerous. This is also interesting if you get into the idea of big data, because we've now tested a couple of thousand people with this, and we can see where people are on the fatigue spectrum. So we don't just have to measure you relative to yourself and build up these baselines. We can just do sort of a one-off score and say, well, hey, this person's really tired. A couple other things as I wrap up here. So we've developed this capability. We can measure brain waves in a couple of minutes with an iPhone and a cheap device. Well, what's the use of this? Why would you do this? Well, the fatigue management system that I've told you about, But there's a lot of other things you can do with it, and I'm just going to share with you some of them quickly. One is we don't have to just measure fatigue. This is work by a friend of mine at Florida State. At this point, he was at Stony Brook, but Greg's now at FSU. A different neural response can be examined to peer into depression. So we haven't just built a fatigue detection system. We've built a brain health and performance detection system, and we could also measure depression, for instance. We're in discussions with the government because we could also potentially detect cannabis inebriation. So right now, there's no great roadside test for cannabis inebriation, and we could potentially use this technology to detect that. Concussion. This is work we're already doing with Rugby Canada. These brain performance scores are very different when you're concussed, and as you recover from concussion, they get back to that healthy baseline that we can measure. So we've also built a concussion detection system. And this is one that was in the news a little bit, but we're working with a couple of groups here. We also believe that we can track mild cognitive impairment and dementia and the progression into things like Alzheimer's. So you could imagine that as you get older, you might not do this kind of test every day, but you could do it every month or every couple of months, and it would be a way to track whether your brain health is doing just fine or whether your brain health is suffering a little bit. And right now, this is hard to do. If you want to get a dementia or Alzheimer's assessment, you need to go in and see a medical doctor, and it's quite an involved process. Potentially, this is something you could even track at home. And it doesn't always have to be negative. A lot of people think it's only a negative technology. Another former graduate student of mine, Anthony Pluta, used this technology, and he was able to show that he was able to predict baseball batting performance. So you could use this with athletes to see when they're doing well or doing poorly, but then you could give them feedback potentially to get their brain into a spot where they perform better. So in terms of NASA, what's next is we currently have a fairly large grant under review because we're not going to go back ourselves and go in, but we want to extend this and use our tech on some of the next long duration missions for 6 months to a year. And if that's successful, we want to get our tech up to the International Space Station so the astronauts up there can use it to monitor cognitive fatigue. And of course, if that goes well, hopefully one day the tech we develop will go to Mars as a part of the Mars mission. So thank you for listening. There's a lot of different players in this. There's funding from the Canadian government. There's the company behind the technology. There's, of course, the people in my lab. There's a couple special thank yous. Dr. Kim Binstead, who is the principal investigator of the NASA High Seas project in Hawaii. Dr. Gord Binstead, my collaborator, who's actually Kim's brother. He's at UBC Okanagan. Dr. Kent Hecker at the University of Calgary. Dr. Graham Moffat, who is the Chief Science Officer at Muse, which is Interaxon Inc., and Mr. Mark Aldrett, who is the CTO for Suva, who built the Peer app for us so we could do this. And of course, there's this. Whenever I give these talks, there is a wealth of people that have collaborated on these experiments at the University of Victoria, at the University of British Columbia, and at universities across Canada, United States, and the world. So I'll stop there. Thank you, and happy to take questions if I can figure out how to stop the screen share.
All right, Olav. Thank you very much indeed. Now, of course, one of the things we pride ourselves on in Café Scientifique is the interactivity with the audience. So what I'm going to do at the moment is I'm going to give everybody back their audio permissions. And so to our audience, I'm going to request you now to turn your microphones on. And let's, in 5 seconds, give Olav a big round of applause, a big real round of applause.
How do I stop the screen share? How do I stop the screen share?
So let me kind of tell you guys how the questions are going to work. I had a little bit of feedback last week. So what I'm going to suggest is I'm going to sort of just talk with Olav for just a minute or two here. But please use the chat window don't feel you have to write a long question, but if you want to send a comment or a quick question, use the chat window using the button in the bottom right of your window to open it up and click on the speech bubble, and then post your questions, and I'll try to get through them sequentially. We've got a few minutes here to get through them, so there's no rush, but I know it takes a moment or two to actually do the typing. There was one first question I wanted to ask you, Olav, and
Yep.
you've got some great and really incredible things going on. But I also thought of a much more down-to-earth application. Is one of the big questions in education is how can we, best teach our students using this really kind of old-fashioned method of standing up in front of them and talking to them. So have you have any projects where you've actually sort of looked at cognitive performance in an education environment?
We have we've played around with it a bit. One of the things that we're in, it's probably not exactly what you mean, but one of the things we do have some data where we are measuring brain performance prior to taking tests, and we found that much like the baseball study, we were able to predict with a reasonable degree of certainty how someone was going to do on a test before they wrote the test. But we haven't done what you said, which is it would be pretty easy with this kind of technology to put it on a bunch of students and monitor what's going on there. And we kind of do that with another project we have. So I've got a NASA project that I can't really talk about because a nice gentleman from the FBI asked me not to. But let's just say that with this tech, you could potentially monitor whether someone is vigilant or not, paying attention, engaged. And in a classroom environment, that'd be kind of cool because you could imagine you could do different teaching styles or different things, and you could use that technology to assess those.
So I noticed you're still sharing your screen, Olav. So
yeah, how do I do that? I'm trying to figure out how to close that, to be honest.
I'm just looking for you. So you want to go to the original window that you started from, I think.
Yep.
The little square with the arrow in it in your panel on the right. So there you go. There should be a stop sharing option.
Oh, there it is.
There we go. Okay, that's cool.
Sorry about that. Really, no wonder people were leaving. That's a bad thing to put on the screen.
No, that's fine. That's fine. So we've had a few questions. Let me just go through these. So Jim Hesser actually asked the first question here. Have you been able to conduct any interesting research related to COVID-19 isolation that people are going through? We're doing the ultimate big data experiment right now.
So we actually talked about this in principle, Jim. That's a great question. In the sense that we really, if we could mail out muses and iPads to everybody, and it would be interesting to track changes in brain health and performance as we go through this. I've been tracking my scores a little bit, but the problem is with a sample size of 1. In fact, I've got my muse right here beside me. I basically put it on every day and I do the assessment. The problem is when you've got a sample size of 1, it's very hard to see anything. So I wish we could have, but we haven't. We have talked about that, and this is in my research group, if this was for some reason to go into a second wave, and let's hope that that doesn't, I'd like to be in a place to deploy something where we could monitor people if that happens.
So another comment we got was with regard to the answer you gave on education, that you guys could put Rate My Prof out of business.
You could. I guess you'd. It's really funny because when we've talked about this in principle. The question, of course, would be, and John, you might appreciate that. Do you really want to know how bored they are?
Yeah. It's sometimes better to just carry on regardless.
Yeah, no. On a serious note, I think there's so many uses for the tech. The biggest problem we have is trying to find time to do all of it.
What I was really interested in is with this question about education is you've now solved one of the most difficult problems for neuroscience, which is how to make it experiment driven in real context. Yeah.
Yeah. Well, that's I don't. A lot of people don't know this, but I don't have the traditional path to academia. I was a high school teacher, and I went back to school because I asked, and I didn't even think I was going to get a PhD. I just asked a lot of annoying questions about how people learn, and next thing you know, I'm a neuroscientist. But because of that, I've always been concerned about ecological validity, which is how does this stuff hold up in the real world?
Mhm.
Because I can tell you from experience, you can see an effect in a lab, in a very artificial sort of experiment, but is that what actually is going on in the brain when people do these things in the real world?
Sure. So looks like we have one final question. This is from Dave McMurtry. And he was asking quite a specific question, but he says the fatigue effect that you observe seems to occur on the second phase of the response curve, but not so much the first. Is this telling us something? I'm not
Yeah,
exactly sure what he's talking about, but I thought I'd put it to you.
I know exactly what you're talking about, Dave. Basically, those little bumps have different meaning. The first bump, the one that's not affected, is the M200, and it just basically means that the neural processes there aren't affected by cognitive fatigue. Um, so what it means is some of the things we measure are and some aren't. What's interesting is that earlier bump that wasn't affected by fatigue is sensitive to depression. So if you had someone that was depressed but rested, you'd actually see the opposite pattern. You'd see a reduction in that bump, and you would see the other bump would be in line. So you can study these patterns. Now, it gets a bit more complicated than that. We end up using a lot of machine learning techniques to not just look at these bumps, but look at the overall pattern. But it's an excellent point. But yeah, basically it just means that second cognitive process isn't sensitive to cognitive fatigue, or the first one isn't, but the second one is.
Okay, so we're just to let people know, I'm going to wrap this up around about 7 o'clock. So we'll just have a couple of more quick questions, and I'll give you a brief
Yeah.
advertisement for our May talks before we wrap up this evening. So a quick question from Jean Dragushan. Can someone fool the test?
Gene, excellent question. No, you can't. If you think back to where I showed you the time course of the neural response, this brain response is happening in a couple hundred seconds, and it's a natural response. So even if you know those circles are coming, the order is always random, and we actually change the colors between game sessions, so you sort of learn what the target is every time you play. But you can't really fool this because it's so fast. One of the nice things about this test is I actually didn't even need to tell you anything. If I had have just shown you those circles, you would have naturally had a larger brain response for the green one than the blue one, just because it's rare. So it's actually the underlying neural system is just detecting frequency in a sense. And it can be even easier than that. When we do this with cannabis impairment, we realize that people might not want to look at screens, for instance. So you can just do it with sound. So for instance, if you just play boop, 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 beep, boop, 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 beep, you're going to get a different brain response for the beep because it's rare relative to the boop. So you can make this foolproof.
Cool. So let me just do one last question. This is from Steve Nicole. Uh, and essentially, I'll just read the question to you. Is there a potential to design a longer term experiment to detect the early stages of burnout in healthcare staff, perhaps using trended increases in fatigue and low mood over time? So I guess like the experiment you did with in the mine camp, but looking over an extended period.
Yeah, Steve, excellent question, and that's something we've talked about. When we did both of our island health studies, the one with the clinical simulation and the one in the hospital, they were both just over a couple of days. Really, the problem with these things, if I'm being honest, comes down to research funding. Funding long duration extended studies is quite expensive. But our MCI study that we're kicking off, for instance, is going to run over 2 years. Um, we just don't have any funding in place, sadly, to do the fatigue study over an extended period of time like that.
Well, we've had a wonderful evening, everybody. Thank you for joining us. Thank you again to you, Olav, for a wonderful story and some great work. And let me just let those of you watching know what to expect next. So it's our normal way of operating in Café Scientifique is we give talks on the second and third Tuesday of every month. and that's what we're going to stick to. So expect to hear from us in May, the second Tuesday in May, the third Tuesday in May. I forget the exact date, but don't worry. I'll be sending an email to the Café Sci email list over the next couple of days with advertising our next couple of talks, what to expect. And hopefully in the next couple of days, I'll also be able to send you a link to our videos on the UVic Great Indoors project as well. So you can send the videos to friends and family or colleagues and watch again, and we will keep it going. So thank you again for a lovely evening, and thank you, Olav.
And thanks everyone for signing on to watch. I really appreciate it.
All right. Thanks, everyone. That's our wrap up for the evening. See you in May.
Good night.
Thanks, Olav.